So we've reached the point where we're able to look at the graph of a derivative and understand everything that's happening with the original function. And remember, we're always analyzing what the original function is doing. But now we're going to be able to also add to this concavity. Are you ready? Here we go. Okay, now, first thing to understand is this is the graph of a derivative. That means that this graph is describing things that have to do with slope. And that's still going to be our primary conclusion. That is, when you look at this graph, you see certain values. You see certain y values. And when you see these y values, which of course I'm highlighting the positive ones, what you are actually seeing would be the slope of the original graph. And it doesn't hurt to kind of go back to the number line and understand that the x-intercepts of this graph are going to be the critical points of our number line, because that's the place where we see the positive slope occurring to the left of -2 and the positive slope occurring to the right of 7. And, of course, we also see some negative values. Now, those negative values would represent negative slopes. Now, you should be looking at what I just did and saying, okay, Miss Naylor, that's what we did in the last section. Yeah, it's exactly the same. Nothing has changed. So are you ready to analyze this for the concavity? Here's the thing. The concavity is the second derivative. In a sense, that would mean that it's the slope of the slope. Now, do you understand that I'm starting with the derivative? So I'm starting with the first slope. So now I need to think about the slope of this graph. I mean literally the type of tangent lines. Now, every one of these tangent lines that I drew right here, you should say are negative. Well, what that means is that I have negative concavity. And in a similar fashion, over here on this side, every one of these slope lines that I'm drawing in blue, you should say are positive. What that means is that I have positive concavity. So where's the inflection point? Where's the point, the critical point that I put on this second derivative number line? That's right. It's the extrema of the derivative graph. The critical point, the inflection point, is the extrema of my derivative graph, so that I can say that everything on the left of -1 had negative slope, everything on the right had had negative concavity, and everything on the right had positive concavity. And now we're able to think about and analyze our original function. Now, I tend to like to be visual. I like to graph my function. I want to see the function that goes up, like it's always gone up. I want to see the function that goes up until it gets to a maximum of -2. I want to see the function that goes down until it gets to a minimum value of 7. Now, do you realize that what I'm doing here is I'm drawing my graph based on the slope, kind of the main type of thinking here, because then I'm just going to draw a graph that goes up to the right of 7. But at the same time, I've also been able to satisfy the concavity, because I'm concave down everywhere to the left of -1, and I'm concave up everywhere to the right of 7. Okay, so does the concavity kind of fit with what we already predicted? I would say so. but we're still able to look at this derivative graph. And in a sense, we're actually looking at the slope of this slope graph. And that's how we're able to come up with a negative concavity to the left of -1 and a positive concavity to the right of -1. By the way, you would still make a nice list of answers. I should be a good model and make sure that I'm showing you that I would expect you to say that there's a maximum at -2. Obviously, there's a minimum at 7. I've got my increasing and decreasing. That was, once again, based on the slope. So it looks like it was increasing to the left of -2 and to the right of 7. It was decreasing in the middle of these numbers. And then we get over here and we can talk about some inflection. That inflection point, of course, is occurring at -1. And then we've got concave up, which was to the right of -1, and then concave down to the left of -1. By the way, no y values. Yay! Yeah, there's no y values because, because you don't have the actual original function. And therefore, even though I drew the original function right here, I really don't know exactly what height it would be at, and it doesn't matter. What do you think? Do you think you can anticipate what the original graph would look like? Do you think you can add the concavity? It's a good problem. If we were in class, you guys would be trying this on your own. So I'm going to encourage you to pause the video and do what you need to do. Maybe you need to think about some number lines. Maybe you're the type of student that you're just ready to jump right into drawing the original function. But I encourage you to do that thinking right now. So you should have concluded that there's an awful lot of positive y values on this graph. In fact, there's actually positive y values everywhere except at 3. It is important to note that 3 is not positive or negative. And so, what is 3? Well, it wouldn't be a maximum or minimum because I don't have a switch of my slope. Again, my slope doesn't switch, it stays positive. But if you think about the slope of this line, you would come to the conclusion that at at 3, that is changing. That is changing from negative to positive. Now remember, the yellow negative sign actually refers to concavity. The positive blue sign actually refers to concavity. So what does my original function look like? It's a little different, isn't it? It's a graph that's always going up, except at this one point where the slope is actually equal to 0. And yet it's concave down for a while, and then it switches to concave up. So what does my original graph look like? Are you thinking about a graph that always goes up? That's the first thing to picture. But as it goes up, it actually needs to be concave down. Now, if I draw a graph going up, but it's concave down, it would have this type of curvature. If I draw a graph that's still going up, but is now concave up, it would have this curvature. So how'd you do? That's right, x equals 3 would be an inflection point. And technically, it would be a place where the slope is equal to 0. Just at that one moment of time, the slope is equal to 0. So it does satisfy the first derivative. But, of course, there is no maximum or minimum. Now, it's not against the rules to be thinking about the algebra calculus connection behind these problems. You see, the type of graph that we just drew here is definitely of the power of 3. It's some type of x cubed. The derivative graph that we started with, well, yeah, it would have to be of some type of x squared. So we definitely have the right connection here where the exponents are changing either by going up as I go back to the original function, or the exponents are going down as I go to the derivative. So you're welcome to add these levels of insight. Of course, we will continue to add that as we walk through this year. I've got one more, I suppose you could say, kind of thinker question. It's the kind of question where, again, you're going to excel if you think about this before I just show you. So, are you ready to think? We've got the derivative. Okay, that's this first statement. The derivative is negative. Now, if we just stop right there before we go anywhere else, that means that the graph is going to be going down. The graph is going to be decreasing. So there's lots more to come in this problem, but let's make sure we understand that this so far will have to be true. Except at x equals a. At x equals a, it says that the derivative is equal to 0, which would mean that we have a horizontal tangent line at that one moment. Are you starting to picture the graph? Remember, it's a graph that goes down. So what about this next statement? It says that the second derivative is positive. The second derivative is positive. Right, that would be concave up. Are you picturing something concave up? And then we've got the second derivative being negative. And, of course, that would mean that we're concave down. Now we've got one more statement where it says that f double prime is equal to 0 when x equals a. So the important thing to understand about this problem is that x equals a seems to be some type of critical point. What type of critical point? Well, if you think about a graph that's going down all the time, then x equals a can't be a positive or can't be a maximum or minimum. So how are you going to draw the concavity based on x equals a being an inflection point? X equals a is that inflection point. Positive concavity to the left of a. How'd you do? Positive concavity to the left of a. Negative concavity to the right of a. Okay, what we have here is another example of what sometimes students will call like half of the concavity. You see the blue section I drew is concave up, but it just doesn't continue on the other side. In a similar fashion, the red section I drew is concave down, but it just doesn't continue or didn't start on this side. But that's all right. It still has the concavity. The graph is going down. I have an inflection point, and what we just drew here would be the graph of the original function, which is actually some type of negative x cubed. Well, we've learned how to analyze an original function for its extrema, increasing, decreasing, inflection points, and concavity. Your assignment is purposely a little bit shorter, that you can really focus and do a nice job on a few less problems, making sure that you're not using a calculator as appropriate. Normally, the second half of the assignment, calculator becomes a little more necessary, and then we have a couple fun problems near the end. But before you do any of that, there's the exit ticket. So do a nice job, and that wraps up the first half of this chapter.